Here we're going to take a look at a slightly more typical example that involves an integral with an inverse trig function. Now, when I say that, I don't mean that the integral has an inverse trig function. I mean that the integral will give us an inverse trig function. Now, what typically happens with these guys is they don't initially look like inverse trig integrals. They look like, I don't see any trig functions at all in this guy. So there's got to be something that hints to us that this might be an inverse trig integral. The first time a student looks at an example like this, what's a very natural thing to do, they might think the log rule because you have the fraction. You might remember from Calc 1, if you had the integral of like du over u, then this integral was the natural log of the absolute value of u. Now, that's a good thing to look at, and it's a possibility, but I don't think that's going to be it, because if we looked at this expression here in the denominator, if this was our u, then the du would be 2x minus 6, and in our numerator we only have a 1. We don't have a 2x minus 6, and we can't make a 2x minus 6 because there's no x's at all. You can't fix variables like you can fix constants. So it's worth a look, but it's not going to be it. So what comes next? What should our mind go to next? Well, the next thing that would go through my mind is that this vaguely reminds me of the arctan integral, because again, it's a fraction, and I've got something squared, and then I've got addition, I've got some other terms or whatever. It's not an exact match, but it looks roughly like that, at least enough to pique my interest. So let me see if I can somehow turn this or mold this into this form right here. Now here's the big thing. This denominator is not currently something squared plus something squared. So here's where an algebra technique is going to come in that we should be fairly familiar with. It's called completing the square. Completing the square. If it's been a while since you've had a pre-calc class or an algebra class where you learn completing the square, it would be worth your time to go back and review this process here. But I'll give you a quick little crash course. Nothing super thorough, but at least enough to get us past this problem here. Okay, what we're going to do is we're going to complete the square on this denominator, and it's going to turn into a sum of two perfect squares. So what we're going to do is we'll take x squared minus 6x, x squared minus 6x, and this doesn't factor perfectly, but there's a number instead of 13 that we could put at the end that does help it factor perfectly. Now, hopefully you know what that number is. Think to yourself, do you know what number we should put here? All right, the way that we get this number is we take half of this constant, the coefficient of x, which would be -3, and then we square it. So if this is ax squared plus bx plus c, you take half of b and square it. So half of -6 is -3. -3 squared is 9. 9 is really the number we want. 9 is really the value that would turn this guy into a perfect square. Now, what happens to the 13? Well, the 13 has to stay there. We can't just drop the 13 because we want to. Matter of fact, we can't just add 9 because we want to add 9. This part right here in green, that's changed the problem. So what I do is if you add 9, we're going to turn right back around and subtract 9, and that'll keep everything balanced. That way this denominator hasn't really changed. All right, so if I rewrite my integral now, this will be the integral of 1 over, all right, let's factor the first three terms. Having a 9 instead of a 13, you notice it factors perfectly. This would be x minus 3 quantity squared, and then take minus 9 plus 13, that's plus 4 dx. So it simply looks different. It's not different other than just aesthetically, other than just the way that it looks, but really these two guys are equivalent. Now, why would I prefer to write it this way as opposed to this way? Well, take a look here. I have 1 over a squared plus u squared. A squared plus u squared. A squared is the 4 because it's the constant. U squared is the x minus 3 squared because it has the variable. All right, so let me flip over to the next page here real quick. So let me rewrite that just so I have it here. So I have 1 over, I'll write the 4 first, and then the x minus 3 squared, just so that they're in the right order. The u is x minus 3, and the a is 2. So this perfectly fits, again, perfectly fits this arctan template, right, that I've created. So really it's plug and chug. I'm basically done with the problem. This integral is 1 over a, right, 1 over a, arctan, right, arctan of u over a plus c, right? And that's this guy's indefinite integral. This is how we do it. You basically set up the template. That's the hardest part. And then once that's done and you've chosen your u and your a, you simply fill in the blanks. And really that's all there is to it. Now, there's a key to this problem though, and I can't stress this enough. If you did not know completing the square, to say it frankly, you could not have done this problem. And so much of your old stuff that you've learned in other classes up to this point is going to be so critically important to keep reviewing and keep practicing, old, algebra examples and different things that you've done in previous courses. Now, if you don't know what to study, if you just kind of say, well, maybe I'm rusty, but I don't know what I'm rusty at. The only way you can do well in this class is by practicing lots and lots of examples. Just go through the textbook, start with the easy ones and plow through to the hard ones. And if you do enough of them, you'll run across most of the typical types of, I hesitate calling them tricks, but you'll run across all the typical types of examples that use things like completing the square and these, these little things that you may not have thought of if you didn't see them first from someone like me. So anyways, hope that helps a little bit. We'll continue to do some more of these examples if you want to go ahead and fast forward to those videos now.